One of the most common programming tasks involves finding if a specific value is either in or not in a list. Sometimes we're also interested in determining where in that list the value is found. Because this task is so frequent, and because the amount of data that we search every day is so large, it makes sense to try to find the fastest and most efficient way to locate the item we are searching for. Searching is something that we do every day, not just on a computer, but also out there in the real world. So let's start by thinking about searching in a physical sense. Let's say that you had a stack of boxes, and you needed to find an item, and that item was located inside one of those boxes, or possibly not located in any of them. How would you do it? You would start with one box and check inside of it and see if the item was either in the box or not in the box. If it's in the box, then great, you're done. But if it's not in the box, you would move on to the next box, and you would repeat this process until you have either found the item that you're looking for or you have run out of boxes. As we begin searching for things on a computer, this is the first approach that we will try. We are going to begin by having an array or a list of data. For now, the contents of this array will be integers, but there is no particular restriction on the type of data that we can be searching for. For this particular example, our list of data will be 10 items long, and you can see an example of that down here below. We have 10 items, 7, 5, 2, 1, 4, 9, 0, 3, 6, and 8. Using our box analogy, how many boxes will we need to search until we find the item that we're looking for in a list like this? The answer, unfortunately, is it depends. And that's actually the answer for many of the different types of searching problems that we will experience in computer science. What exactly does our search problem depend on? Well, part of it is the value that we're searching for. So for this specific example, if the item that we're searching for is 7, and we start at the beginning of the list, we find it right away. It's in the first box. But if the item that we're searching for happens to be something like 9, then starting from the beginning, we have to search through the first 6 boxes in order to find it. What if the number that we're searching for is something like 13? In that case, it's not in any of these boxes, and we won't know that until we've gone through every single box. The sequential process that we just described is what's known as a linear search. To perform a linear search, we start at the first item in the array or list, and we check to see if it's what we're searching for. If it is, then we can return the value or the position in the array, depending on what it is we're looking for. If it's not the thing that we're looking for, we can move on to the next array index or the next position, check it, and repeat this process until we have either found the item or we have run out of items. Let's examine some pseudocode for implementing a linear search. In this example, we're going to call our list of items L, and L will have n items, and these items will be numbered or indexed L0 through Ln-1. The value that we are searching for is going to be called T. For this specific implementation, if we find the item that we're looking for, we are going to return its position in the array or list. If we do not find what we're looking for, then we will return -1, which in most languages would be an invalid array index. And so we can use that as an indicator that the search terminated unsuccessfully. Our algorithm will begin by initializing a counter. In this case, we're calling it I to 0. And we will have a loop that uses that counter to run through all the possible array indices. So starting at 0 and continuing up through n. Notice that we have a less than n here, which means the actual value n will never be a valid array index. Because we are in fact starting at 0, our last array index, our last valid position, is actually n minus 1. Inside our loop, we are looking at the list or the array of data at position I and checking to see if it's equal to the value that we're searching for, what we're calling t. If it is, then we can return I because that is the current position. If it's not what we are looking for, then we're going to increase I by 1. And this effectively allows us to search the next position in our list or array. We continue this until the loop is done. If we happen to end the loop without having returned, then that means we didn't actually find a situation where the item we were searching for was in the list, and so we can return -1 at that point. Using the array that was displayed earlier, if we were searching for 9, the linear search would start at index 0, which is where our 7 is stored, and would increase until it finds the 9 at position 5, and it would then return that position value. If we were searching for the value of 13, our linear search would once again start at the index of 0, where the value of 7 is, and it would increase until we go past the end of the array. At this point, if we've gotten past the end of the array, then we know that the data that we're searching for isn't in our array, and so at that point we can return -1. Whenever we analyze an algorithm, there's a variety of cases that we might be interested in. One such case is what we call the best case. This is the case where an algorithm performs at its most efficient. For a linear search, the best case will occur when the item that we're searching for is in the very first location. So for this specific example, if we were looking for the value of 7, we find it right away at position 0, and thus it only requires one comparison. Most of the time, we're not going to be that lucky. And so one of the other cases that we like to examine is what we call the average case. And the average case generally represents what we will typically see for most data sets and inputs. Assuming that each element or each value is equally likely to be searched, a linear search will take on average the ceiling of n+1 over 2 comparisons. Some of you might not know what I mean by the ceiling. The mathematical operator that you see here in this expression that looks like two vertical lines with some slight horizontal lines kind of poking out of them at the top. This is your ceiling operator. And what the ceiling operator does is it gives you the smallest integer value that is greater than or equal to the value that's inside of it. So if you did n+1 divided by 2 and you got an integer value, then effectively your ceiling doesn't do anything. But what happens if the n+1 divided by 2 gave you some decimal fractional number? Well, we're interested in integers because you can't just have a fraction of a comparison. If the n+1 over 2 gives us a decimal value, we do have to account for that comparison. Even though it's coming up as a fraction of a comparison, the reality is it's a full comparison that we're making. It's just the sort of a nature of dividing by 2 that sometimes, if it happens to be an odd number, you're going to get a 0.5 in there. And so what we're going to do is you can think of it as rounding up, but ceiling is actually slightly different than just rounding, because normally with rounding, if you have a value like 3.8, you would round it up to be 4. But if you had 3.2, it would round down to 3. So usually we use 0.5 as sort of the break point for whether or not we're rounding up or rounding down. With ceiling, there is no breakpoint. So anything greater than 3 will be rounded up to 4. So 3.9 would become 4. 3.5 would become 4. 3.00001 would still become 4. Later on, we'll see that there's another function called the floor function, which notationally looks identical. It's just sort of reversed. That kind of does the opposite. And so if you have a value like 3.9, the floor of that is 3. And you can think of that as just truncating the decimals. Although it might seem a little bit strange, as a computer scientist, the case that we are actually the most interested in is the worst case. This is how long our algorithm will take when given the worst possible combination of data and inputs. For something like a linear search, the worst case is going to occur when we're given a list of data and the item that we're looking for is not in the list. And the reason why that's the worst case is it forces us to look essentially in every single box before determining if the item is there or not. There's really no sort of shortcut way out of that. And so that requires the maximum number of comparisons for this algorithm. Let's get a bit more specific and formal about what this worst case time actually is. If the item is not in the list, and we have n items, then it's going to take n comparisons to verify that the item is not in the list. Thus, for n items, it's going to do n units of work, where for this problem, the unit is a comparison. We typically use the worst case for all of our big O analysis, and for something like a linear search, this means that our worst case, our big O for linear search, is going to be big O of n. Not only are we thinking of linear search as going through a line of items, but it's linear in the sense that the function grows as a linear function. We have previously seen a graph demonstrating what these linear growth functions look like. As the number of items that we're processing goes up, the amount of work goes up in equal proportion. A linear search might seem like a natural way to search, and it might even seem like the only way to search, but there are often faster algorithms that we can use that will be more efficient than O of n. Even though there might be faster algorithms, though, we still will oftentimes use linear search for a variety of reasons. Part of it is because it's a rather simple algorithm to implement. It's very simple for even a beginning programmer to put together a basic working linear search. And for small sets of data, this is often a fast enough search. And what you're going to find is that if you do empirical analysis on your algorithms, for data sets that are relatively small, so less than 100 items or so, linear search will oftentimes be the best performer. As the size of n gets larger, then it starts becoming worth our time to investigate faster and more efficient algorithms. Let's revisit the idea of searching using the physical box analogy. Let's assume that the object that you're searching for is large. It would be obvious that the box that you're going to put it in would have to be at least large enough to hold that object. And so that means if you had smaller boxes, you could skip over searching them because there's no possible way that the object could fit inside of it. And depending on how many items you are trying to search through, that could be quite the time savings. If the boxes were somehow arranged in order of size, you could very easily skip a large number of them. If they're not arranged by size, then you're still going to have to at least look at the box to make a judgment, and determine if it's large enough to hold the object, and that is something that you could effectively consider to be a comparison. For another real-world analogy that we can compare to our searching problem, we can look at house numbers. So on any given street, every house will have a number assigned to it. And as you're driving down the street looking for a particular number, you don't necessarily have to look at every single house. You can drive for a while and skip over a bunch of them and then take a peek. And the reason why you can do that is because those numbers happen to be in numeric order. They're sorted. So this allows you to quickly eliminate a large number of houses when you're looking for a specific house. It also gives you the ability to know when you have gone too far, because the smaller number that you're looking for couldn't possibly be beyond the larger numbers. So it does save you from having to check the number of every single house. In fact, it allows you to eliminate most of them. We might be able to take advantage of that as part of a search algorithm. We're going to try searching through our list of data one more time. This time, we are going to be working with a list of data that has already been sorted. Unfortunately, sorting is not magic, and it does require some work to make that happen. We are actually going to spend a lot of time this semester talking about how to sort data. For right now, let's just assume that the data that we're receiving is already in some kind of sorted order. Another thing that I want to point out about this specific piece of data here is that now that our numbers are sorted, it also means that our values happen to be located at the same value as the array index. So for example, the value of 3 happens to be at array index 3. That is just purely a coincidence in this example. In the real world, your array indices always start at 0 and go up through n-1, but the values that are in your list could be anything. In fact, they don't even have to be numeric. We will begin by trying to perform a linear search on a sorted list. Does being sorted make any difference? Unfortunately, the answer is going to be no. In the worst case, a linear search is going to remain O of n. You could even try starting at the end and working its way backwards. Maybe you're thinking that the value you're searching for is larger, so starting at the end might help you find it faster. But the worst case is the item's not on the list, and so you would still have to traverse all n items. On a related subject, I said maybe the item is large. In this particular data set, our values are 0 through 9. 9 is not really a large number. It's pretty often the case that you're going to have values in your arrays or lists that will be hundreds or thousands, or in some cases, even in the billions. And so it's entirely possible that the values that you're looking at are unpredictably large, or in some cases unpredictably small if you had arrays or lists of floating point values. And they can even be strings. They could be pieces of text. So it's not always easy to make predictions about the contents of your array, and that's why we can't really rely on those kinds of predictions when we're looking at our data. In this case here, the only thing we can run on in terms of assumptions is the fact that this particular set of data is going to be sorted numerically. As long as we have data that is sorted, then instead of using a linear search, we can try a new algorithm that's known as a binary search. And in this case here, binary doesn't necessarily mean like zeros and ones, like you maybe have heard as like base 2 numbering. In this case here, binary means having two parts or being subdivided into two parts. And the reason why we're calling it that is because as part of the searching process, we are going to be splitting this list in half. So instead of searching at the beginning of the list and beginning there, we're actually going to start our search in the middle. Believe it or not, picking the middle element isn't always as easy as it might seem. If we have an odd number of items, it's actually quite easy. You're going to have a middle element with an equal number of elements on each side. But what happens if you have an even number of items? You can't actually pick a position that's halfway through one of your elements. So in order to make this work, we do have to come up with sort of a process for choosing that middle. And the way we're going to do that is by summing up the sort of the beginning and the end of our array, and then dividing by 2, and using that floor function that I had mentioned earlier. We are going to use 3 variables to keep track of various locations within our array. One is called left, and another is called right. And initially, where these things are going to be located is the leftmost and rightmost positions in our array, effectively the first and last position. To find the middle, we are going to compute the left plus right values, so taking the index of the leftmost and the index of the rightmost, and then divide it by 2 and take the floor of that. So in this case here, if we're adding 0 plus 9, and we divide that by 2 and we take the floor of it, we get 4. And so position 4 is going to be where our middle variable is going to be pointing. It might seem a little bit weird to have a left and a right here, because it seems at first as though those things won't ever change. But as it turns out, that's not going to be the case as we progress through this algorithm. We're going to start our search for the value of 6 in our array. So we have set up our left, right, and middle values to their default starting positions. The middle index is 4. And so what we're going to do is look in that position and see if the value stored at that location is the value that we're looking for. And unfortunately, in position 4, where our middle is currently pointing, it has a 4, not the 6 that we are looking for. This next piece is what really separates the binary search from the linear search. We were looking for the 6, but we found a 4, so we know that we need to keep looking. But because our list was sorted, we can look at the value we're searching for and compare it with the thing that we found, and based upon whether or not it is less than or greater than the value we're looking for, we can eliminate one entire half of the list. In this specific case, because the value that we're searching for is greater than what we found, then we can eliminate the entire left half of the data because we know those things are going to be also smaller than what we're looking for. And that's because the list was sorted. We can make that assumption. Essentially, the trick behind binary search is to avoid searching data that couldn't possibly contain the value that we are looking for. We still haven't found our value yet, so what we're going to do is search the remaining half of the array. In order to set this up, we are going to adjust the left or the right and then recalculate the middle and repeat the process that we just did. In this particular case, because we eliminated the left side of our data, the left side of our array, we're going to update our left value to be the middle plus 1. If it had gone the other way around and we had to eliminate the right side of the data, then what we would do is we would change right to be equal to the value of the middle minus 1. Now that the left or the right has been updated, we can now find our new middle by once again using the floor of left plus right divided by 2. In this case, our new middle is now at position 7. But we still haven't found what we're looking for, because we're looking for a 6, and at position 7, we currently have the value 7. Because we found a value that is larger than what we're looking for, we are now going to eliminate the right half of what's there. We have now wiped out our middle and all the positions to the right, and we can once again update our left or right to their new positions and recalculate the middle. At this point, we don't have a whole lot of values left. As you can see, all that remains of our original data is the 5 and the 6. By repeating our calculations to determine the new middle, coincidentally, it happens that our left and our middle are in exactly the same spot, and there's nothing wrong with that. Our middle is where we are looking to find our data. And so we are still looking for a 6, and so we're looking at our middle position, which is currently position 5, and we're seeing a 5. We found our 5, but we are looking for a 6. So because we found a number smaller than what we are looking for, we can eliminate the left half, which really, there isn't a left half, it's just the middle now. And so that value is gone. The only thing that is remaining now is the value on the right, and it's only one item long. That's where we're going to find our 6. After repeating all of our calculations for left, right, and middle, we now find ourselves in a situation where all 3 of these are pointing to the exact same index. This can only happen if we are down to searching the very last item in the list. In this case, we found the 6 that we're looking for, and we can return the index that it was found at. If you get to this situation and you did find it, it means your search is effectively finished. If we don't find the item that we're looking for in the last place that we look, then the value of the left position will become greater than the value of the right position. And this is an indication that the item we're searching for does not exist in this list of data. What we have now is an unsuccessful search. For the linear search pseudocode, we used L to denote the list of data. For this example, because we have a left value that's going to be denoted by L, we will use A to represent an array of data. L, R, and M will represent the left, right, and middle. N will be the number of items in the array, and S will be the item value that we are searching for. We're going to start off by initializing L to 0 and R to n-1. So those are the endpoints of our array. And while our left is less than or equal to the right value, we're setting M to the middle, which is the floor of left plus right divided by 2. At that position M, if we look at our array and we find the item that we're searching for, then we're done. If not, then we look and see, is it less than or greater than what we're looking for? If the value of our array at position M is less than what we're looking for, then we will update the value of L, the left, to be the middle plus 1. If the array at position M is greater than what we're searching for, then we're going to update our value of R, the right, to be equal to the middle M minus 1. This process is going to repeat until eventually we have, found the item that we're looking for and have returned its position, or our loop has ended. If our loop ends and we haven't yet returned, then that indicates that we did not find the item. And in that case, we can return -1 to indicate an unsuccessful search. Depending on your implementation, returning -1 may or may not be what you want to do. In this case, we're using -1 because it's typically not a valid array index in most languages. There may be other criteria that you choose to use for indicating an unsuccessful search, but the overall algorithm would remain the same. Let's compare the performance of our binary search with linear search. With a linear search, our list of 10 items would have required 10 comparisons, thus making it O of n, or linear. In the binary search that we just did, we searched the exact same list of 10 items and found that we could find the item or determine that it was not on the list in only 4 comparisons. How does this scale up for larger values of n? After each iteration of our binary search, we're eliminating half of the list. And while that might seem like a small number of items now, with a list of only 10 items, the half grows equally as n grows. So a list of 1 million items will eliminate 500,000 items, or 500,000 items, after just the first pass. So how do we express this mathematically? Well, the opposite of cutting things in half is doubling them. And that's really what your powers of 2 do. Every additional power of 2 is a doubling of the number. So what we are looking for is the inverse function of your powers of 2 functions. The inverse of our power of 2 functions are base 2 logarithms. And if you're not familiar with how this works, it's actually pretty easy. The relationship between your powers and your logarithms are as follows. So let's say you had some value 2 to the k, so some power of 2, and that's going to be equal to a value of n. So for example, 2 to the third power, so that's k equals 3, would be 8. You can take those same numbers and rearrange them. Log base 2 of n is equal to k. So if 2 to the k was 8 when k is 3, then that means log base 2 of 8 is 3. The log base 2 of a number is essentially saying what exponent do we raise 2 to that power of to get the number. As another example, 2 to the 8th is 256. And so the base 2 log of 256 would be 8. If we try the binary search algorithm for larger values of n, we will find that, in the worst case, it will take the floor of log base 2 of n plus 1 comparisons to either find the item or determine if the item does not exist. So the big O notations here for our worst case for linear search are O of n, but for binary search it's O floor log 2 of n plus 1. So what kind of difference does that actually make for us? If you weren't yet convinced of binary search being better than linear search, this table should convince you. So here we see a value of n from 10 up to some very large numbers, and we can see that with a linear search, the number of comparisons is essentially equal to the value of n, because it would have to try every possible value or every possible position. With a binary search, you can see that the numbers do in fact increase as the value of n increases, but it's a much, much smaller increase. And that's because for every new comparison, we are wiping out half of what's left. And it's growing at a much, much slower rate. So even at those very, very, very large values of n, the binary search here is only taking at most 34 comparisons. That's really, really good. And so as long as our data is sorted, binary search really does give us a much more efficient way of searching through our data. So why not just always use binary search? Is it always better? Turns out the answer is no. The first requirement that we talked about was that the data needed to be sorted. And that's a pretty big requirement because, as it turns out, sorting is actually really challenging to do and very time consuming. But let's assume that our data is already sorted. Linear search is a rather simple implementation. There's not really a whole lot to do. Binary search involves keeping track of several additional variables and keeping track of their values, performing a variety of mathematical operations to calculate the middle. In general, binary search will always perform better than linear search when n gets to be above right around 100. Below that, the cost of all the individual implementation details might weigh any benefits. In general, binary search is always going to perform better than linear search when the value of n gets to be around, let's say, 100 or so, not an exact number. Below that value, the cost of the implementation details might outweigh the benefits that you're getting from the more efficient search algorithm, just because all those little things that we're having to do extra, they do take some time. So like a lot of things, there's sort of a trade-off there. We saw that before when we were looking at summing the first n integers. Technically, to sum the first two integers, it takes less operations to do it the technically slow way when compared to the formula that involves a addition, a multiplication, and a division. But once you cross a certain threshold, once that value gets large enough, the advantages definitely take over. And the same thing is true when we're comparing our linear search and our binary search. For all of these slides, whenever we talk about comparisons, we've really been focused on comparing integers because that's the data that we presented in the lists in these examples. Integer comparisons are generally very fast operations and perform the same regardless of the specific integer that's being stored. If we had data that involved floating point numbers, that's a little bit trickier. Floating point numbers are, by their very nature, slower than working with integers, and because of the accuracy and precision issues, we could potentially have issues with having to test for a tolerance around the target value, so that can also slow down our comparisons. If the data happen to be a collection of strings, well, now the cost of a comparison is going to be entirely dependent on how many characters are actually in the strings being compared. It takes much less time to compare short strings than it does very long strings. Still, binary search on those types of data will still outperform a linear search, but it's important to understand that comparisons are not always equal across types of data and types of operations. As our algorithms start getting more complex, it can actually be very tricky to create a proper and always working implementation. There's a lot of various edge cases that can lead to errors in a program that would otherwise work in most circumstances. As an example of one of these situations, in the binary search, we have a calculation of left plus right divided by 2. It doesn't really seem that there's a lot that can go wrong here, so it seems pretty easy. But what happens if you're working with very, very large arrays? So I'm not talking like 100 items, but what happens when you start getting into the millions or billions of array elements? Well, the values of L and R can get quite large, and integers in most languages do have a limit in terms of how large the values can be. There's like a max value that you can store in an integer or a long int or similar data types. So what do you do if L plus R exceeds the max size of an integer on your platform or on your language? You can get an overflow that can lead to some incorrect values. And in some cases, it's just an incorrect value that you get. In other languages or other platforms, you might get an exception that you have to handle. But either way, in those circumstances, what you now have is a faulty search algorithm. It works well for most values, most scenarios, but there are specific data sets that can be problematic. So what do we do? Well, for a lot of things, we can rework some of our formulas to minimize some of those types of problems. So as an example here, for this left plus right divided by 2, we can actually rework that expression into something that gives us the exact same result, but minimizes the possibility of having an overflow. So rather than doing L plus R over 2, we can do L plus R minus L over 2. Gives us the exact same result mathematically, but we end up getting a value that is less likely to overflow because we're starting off with R minus L. So we're going from a larger set of values to a smaller set of values and then dividing it by 2, making it further smaller, and then adding that to L instead of the first case where the very first thing we did was add L and R, potentially overflowing. So little things like that are things you have to be testing for. It's not always sufficient to test with a small set of values inside of a small array. You really do kind of have to think about what could possibly go wrong, because if it's not going to go wrong today, it's very likely it's going to go wrong tomorrow, and it might not be you that experiences it, it might be one of your users. And so you definitely want to make sure that things like that are covered.